For a low mass star, the evolution of the star after helium fusion begins goes like this. In a low mass star, the core is originally fairly cool. It starts out at 10-15 million degrees Kelvin. It's not cold, obviously, but relatively cool. And it doesn't reach a temperature of 100 million degrees until it gets fairly dense. And it's so dense that the matter inside of the core sort of behaves differently than a normal gas does. And the way that it behaves differently is that it ends up being supported by a new kind of pressure we haven't talked about yet called degeneracy pressure. Essentially, you have the electrons packed so close together in there that you just can't squeeze them together anymore. The result is that when helium fusion starts inside the core of the Sun, it starts very suddenly, and the temperature rises very rapidly as that helium fusion starts, but it takes a little while for the core itself to respond to that increase in temperature. Once it does respond, the amount of energy produced in the core actually goes down a little bit from when helium fusion first started. Now, the big point to take away from this is not details about degeneracy pressure. It's that in a star like our Sun, when the helium fusion starts, it starts very suddenly. Now, what happens after that helium flash depends on exactly what happens as the star is becoming a red giant. In some cases, that star becoming a red giant will lose a fair bit of its mass. In other cases, it won't lose as much mass. And you might ask, well, why is it losing mass? It's losing mass because as the star gets very big and extended, the gas on the outer layer of the star isn't being held to the star very tightly at all. Think the size of this thing, to put it, in the right scale, is that when the Sun's a red giant, its radius will almost be as big as the Earth's orbit. And so, that gas on the outer layer of the Sun there is really very, very far, 90 million miles, 93 million miles from the center of the Sun. And it's easy for that gas to start to escape into space. Now, as with the rest of this course, I've told you a nice story about what might happen. Let's see if it really happens. What you're seeing here is an HR diagram of stars in a cluster. The nice thing about looking at star clusters is that all the stars in the cluster form at the same time. And so what you're seeing is a snapshot of a group of stars that all formed, for this particular cluster, something like 5 billion years ago. And notice that track that I showed you a moment ago in the previous slide, showing how the Sun would change over time, well, you can trace that out in the HR diagram here. There are subgiants that are on their way to becoming red giants. There are stars that are red giants, some that are almost ready for the helium flash to start, and some that have gone through that helium flash already and are burning helium in their cores. The stars down on the lower left, the white dwarfs, that's the kind of star that a low mass star, or that's the kind of remnant that's left behind when a low mass star like our Sun has stopped all of the fusion that it's ever going to do. Now, eventually the helium fusion in the core stops because all of the helium has been converted into carbon or oxygen. And a star like our Sun, its core will never get hot enough for carbon to start fusing into something heavier. And so late in the evolution of, or late in the life of our Sun, the core will look something like this. You'll have a lump of carbon and oxygen in the middle. No fusion is happening inside of that. It's very hot. It might be 200 million degrees or something, but it's not hot enough for carbon fusion to happen. And surrounding that, you have a layer of helium that's fusing into carbon still. And outside of that, a thin layer of hydrogen that's fusing into helium. And outside of that, you have the rest of the star. And take this drawing here fairly seriously. The core really is a very small part of the star here. Now, this what's called this double shell burning, because you have hydrogen burning in an outer layer of the core in a shell, and helium burning in an inner layer of the core in a shell. This never reaches equilibrium, and so what happens is the core heats up, generates a lot of pressure, the core expands out, cools off. Because it cools off, the pressure goes down, the core shrinks again, driving the temperature up, fusion rate goes up, temperature spikes up again, and so the sort of getting these pulses of energy coming out of the core of the star. This affects the luminosity of the stars. You can see in this graph, focus on the part on the right there, showing those spikes. Those are the thermal pulses. And notice that at this point, it's a star like our sun. At this point, its luminosity is 1,000 times what it is today. And during these thermal pulses, you're really drastically varying the luminosity of the star by a factor of, looks like about 5, maybe 10. Now that has an effect on the star. The outer layers of, because what's happening here is every 100,000 years or so, the star puffs out, or less than that, I think it's more like 10,000. The star heats up suddenly in the center. That burst of energy blows off some of the outer layers of the star and makes what's called a planetary nebula. This one that you're seeing here it's called the Ring Nebula. That dot at the center is a white dwarf star. That's the core that was left behind after all of the outer layers of this particular star were blown off into space. Now, these planetary nebulae are very common. They're not all nice round circles like the Ring Nebula. This image is nice because using spectroscopy you can measure the composition of this gas, and it's composed of several different kinds of elements. The oxygen that you're breathing right now, the nitrogen in the air that you're breathing right now, that came from a star. There wasn't any of it made in the very early universe as the universe was forming, as far as we know. That stuff you're breathing, it came out of a low-mass star like our sun that at the end of its life blew its outer layers into space, and the material from that older star mixed with the surrounding gas and dust and got incorporated into the cloud of gas that eventually became our sun and our solar system. It's another example of a planetary nebula, in this case very clearly showing that these things aren't always round and symmetric. Another one. And a final one here. What's interesting about this one is if you look at the outer parts of this planetary nebula, it's more or less round. And then later in the star's life, after it had blown off several layers, you see that it started to blow off gas asymmetrically, so with different strengths in different directions. So to summarize, this is the life track of a one solar mass star. When it leaves the main sequence, because it's used up all of the hydrogen in its core. Now, only in its core. Remember, outside of the core, you have the other 99% of the star that's still mostly hydrogen. But you've used up the hydrogen in the core. The core shrinks and heats. That puffs up the whole star to make a red giant. It continues until the core gets hot enough that helium fusion starts. When the helium fusion begins, the star enters another stable phase, sort of like when it was on the main sequence, but those helium nuclear reactions are much less efficient than the hydrogen reactions, and so the helium burning phase lasts a factor of 1,000 times less than the hydrogen burning phase. Once the helium's used up, once again the star puffs up into a red giant. The difference this time is that the star has carbon at its center that's not fusing. There's a layer of helium around that is fusing into carbon, and a layer of hydrogen around that's fusing into helium. And again, you still got that other 90% of the star out there that has never fused into anything and never will. As the star goes through a series of thermal pulses, it blows its atmosphere out into space in the form of a planetary nebula, and that lump of carbon left behind is called a white dwarf. It's very hot, but it's also very, very small. Our sun, when it becomes a white dwarf, the mass of that white dwarf will be somewhere between half and half the mass of the sun and the current mass of the sun, but it'll be in radius extremely small. It'll be the radius of the Earth. Now we'll talk about high mass stars in a little bit. Their ending is very different. It's much more violent, and what happens inside them is a little more complicated too. Now, all of this will eventually have a side effect on the Earth. As the sun is getting much more luminous, first the Earth's atmosphere will essentially evaporate off into space. The oceans will boil and evaporate into space. Everything will toast, as the title says here. And the sun will get just big enough that probably we'll end up inside the sun. Well, not us, but the Earth. And on that happy note, we'll turn our attention to high mass stars.